Okay. So we're going to kind of just speed through some stuff here. If we had all the time in the world, acid-base chemistry is a huge and important thing to our bodies, especially if we didn't have the chemicals that we have in our body, our chemistry wouldn't happen right, and basically we wouldn't be alive. So understanding acid-base chemistry is super important. Some common properties of acids and bases, and these are just from the notes that I posted yesterday, which would have been Monday, June 1st. So literally just blazing through this, not really hitting on anything here in particular, but I do want to hit on, there's basically two sort of models of acids. And if you want to just jot down a little bit of this that we're going over here, it might be helpful. And again, these are in the notes that were posted yesterday. So there was this guy by the name of Arrhenius, right? And I believe he was Swedish with a name like Svante. And Arrhenius was a guy who came up with the sort of the first idea of what an acid actually is. And he proposed that an acid is simply anything that breaks up and gives an H plus. All right. So the Arrhenius model is that acids produce H plus. All right. So that's why when we studied acids a way back, when we talked about naming them, typically you would have, if I have HBr, right, that would be hydrobromic acid. And the reason it's an acid, okay, according to our guy here, Arrhenius, is this is going to break apart and create an H plus and a Br minus. So anything that creates an H plus in his mind, we call an acid. And then he went a little bit further and he said, then there's this other group of things, and we're going to call them bases. And just like acids produce H pluses, anything that produces an OH, that's what makes something a base. And so typically, if we are talking about the Arrhenius definition of what an acid or a base is, acids produce H plus, bases produce OH minus. And that's just a nice little sort of historical tidbit that's good to know. And it was a pretty good definition, all right, but it wasn't truly correct. And so what we want to do is get to a little bit more inclusive of a definition that wraps around a couple of other types of chemicals that actually behave like acids and bases. So unless you've got an issue with any of that, I'm going to go ahead and move the page. All right. Now, what we're going to end this little tiny part of our lesson with here is the other model of acids and bases, which is called the Bronsted-Lowry model. And what we're talking about here is that an acid is going to be a hydrogen donor. So it's not so much that it's producing the H plus, but anything is an acid if it is a hydrogen donor. So if I look at this particular reaction right here, all right, I've got two substances, hydrochloric acid and water, and each of them have H, all right, but only one of them is actually donating an H plus. And this is what actually occurs when hydrochloric acid is put into water. This is what makes it an acid. You'll notice that the H is kind of stripped off of the HCl, and now I'm left with Cl minus, because it is Cl minus. And what I did was I took H2O and I added an H to it, so it became H3. And then because it was an H plus, the H2O became H3O plus. So what we would do if we're talking about the Bronsted-Lowry model is we'd say that acids are H plus donors. And another way of thinking about it, an H plus is just literally a proton. So some people will also teach this as acids are proton donors. Well, if an acid is a proton donor, then the opposite of that would be a base. And so therefore the definition of a base is something that accepts an H plus. All right. So as we look at this particular example, I've got the NH3 and the water. And you look at it, they both have H's, and this arrow represents the equilibrium sign, which is why we touched on equilibrium right before this unit. So it turns out that this guy will gladly accept an H plus off of the water molecule. And so as the NH3 gains another hydrogen, it becomes NH4, and it's going from a neutral to a +1 because it just gained a +1. When I get rid of an H plus here, if we think about what H2O looks like, here's the O, here's the H, here's the H, right? If I rip off an H, make that go away, what's left behind is OH minus, all right? And so that ties back to the Arrhenius definition we just talked about of something that you have hydroxide creation. So this was a little bit of a better definition. So we usually focus on the Bronsted-Lowry model. And so bases are H plus acceptors, right? Or proton acceptors. All right, so that's just a little bit of background information there. Anything you want to ask about before we move into the sort of mathy part of today's work?
No.
Okay, all right, cool. Thanks for sticking with me here. Now, we'll revisit some of these things that I'm skipping over. We'll revisit those during our last class time, which is on Thursday, all right? But what we're going to talk about today is what is pH and how to calculate it, all right? And we're doing this reasonably fast, Stella. Sorry, so there may be some things here where you're like, I'm not quite sure. So please jump in and ask questions if you have them. So here's what we actually have happening in water molecules, just an ordinary everyday cup of water, right? A liquid water molecule and a liquid water molecule will actually do this sort of an equilibrium reaction, right? And what will happen, and it doesn't happen a lot, right? It happens to a very, very small extent, but it still occurs, and it's important for a lot of chemistry that happens. So one of these water molecules gives up an H, and so it becomes OH minus. The other water molecule takes the H, and it becomes H3O plus. And this is just another way of writing this equation. This is what really happens, all right? What really happens in water. But because of sort of the way that chemists developed things, this is oftentimes used as a little bit of a shortcut, okay? And it goes back to the idea that Arrhenius said anything that creates H pluses is an acid and anything that creates OH minuses is a base. So what we're getting at here is a really important idea that it turns out we can write an equilibrium expression for water. And so sometimes this might even be referred to, and you see this below, it's Kw, right, the equilibrium constant for water. And I'm hoping that you remember when we did the K expressions, if we focus on this top equation, can you remind me, what do we never include in those K expressions? We never include what?
Liquids.
Or?
And
I think,
solids.
yeah, liquids and solids. But do we include aqueous or gases?
Yeah.
Yes, we do. All right, so when we write this K expression for this reaction that occurs, we ignore the H2O, right? Because that is pure liquids. The concentration of pure water never changes. And so what we end up with is an equilibrium expression, right? So I'm going to scooch this down just a little bit, all right? So now we got an equilibrium expression where, and I'm just writing it in two different ways using the OH and the H3O plus, or the OH and the H plus, all right? And it turns out that water at room temperature at 25 degrees Celsius, all right, is always going to have, it doesn't break apart into these OH minuses and H pluses very much. Stella, as you look at this number, is that a really big or a really small number?
A really small number.
Yeah, it's 1 times 10 to the negative 7th, which means here's your 1. You're going to move the decimal over 7 places. So 1, 2, 3, 4, 5, 6, 7. That's the concentration of OH minus. And because the OH minus is coming from the H pluses peeling off, they have the exact same concentration. So that's 6 zeros and then a 1. So what we end up with is this really, really tiny number, but it's super important for all of this acid-base chemistry that if we had a lot more time and we weren't doing distance learning, we'd learn a lot more about. But at the end of the day, the K value, when we did those calculations plugging values in, the K for water is just this. Now, I don't know about you, but that's kind of an awkward number. So what chemists decided to do was come up with a different way of working with this. And it ends up being pretty easy if we use a little bit of a math trick called logarithms. And I'm going to jump over here. And so we're kind of zipping through so that we can get done with this. So if I wanted to talk about what, and I'm just kind of curious, Stella, have you ever heard of pH before? Not that you know anything about it, but you've heard of it?
Yeah, I have.
Okay. Can you, like, where have you heard of it?
We did pH stuff last year in biology.
Okay. Like certain things that happen in the body have to occur at certain pHs. Does that ring a bell?
Yeah.
Yep. Have you ever gone to the store and they sell things like it's pH balanced shampoo for your hair or pH balanced this or that?
Yeah, I've seen a couple of things like that.
Okay, so like this is thrown around, but very few people really, unless you've studied a little bit of chemistry, folks don't tend to know what the heck it is. Okay. And so we're going to have to get out a little calculator. And I'm not sure if you have a calculator, but I'm going to show you one online here. And hopefully we can get that worked out. So what the pH is just an easy way of dealing with sort of crazy numbers. All right. So for instance, if I have a concentration of H plus, all right. So pH is just a way of determining whether we have a lot of H plus or not so much H plus. If I have a lot of H plus, then we're going to be really acidic. All right. If I don't have a lot of H plus, all right, that means that I might have a lot of OH minus, and that means that I'm going to be basic. All right. And I know that some kids describe you as not you personally, but they, oh yeah, that person's basic. It's not a bad thing. Basic is just how much OH minus something has. So what we want to do here, just so that we can wrap this up, is figure out how to calculate the pH and how to calculate the pOH. All you have to do is take the opposite of the logarithm of the concentration of H plus. And I'll show you how to put this in your calculator. So if I tell you that the concentration of H plus is this number, then all you're going to do is type into your calculator negative log of this, and it's just going to spit it out. Put you on the spot here. Have you ever played around with logarithms in a math class? It's okay if you haven't.
No.
No. So this is going to be a little bit new, a little bit tricky, but here's the thing that's really going to kind of help you. Notice how this number is basically, it's kind of close to this exponent. Logarithms are related to the exponents, okay? And the negative sign out front here is what changed it from a -4 to, in essence, close to a +4. In this case, a little bit of a +3.3. So we'll do some practice here, but here's what I want you to know. Acids have a pH less than 7, and bases have a pH greater than 7. And typically acids are going to run from 0 to 7, and bases are going to run from 7 to 14. All right. So what I'm going to do is jump over, and I don't know if you've had a chance to look at the assignment. I covered that up a little bit too quickly. All right. We're going to look at the assignment here today, do a couple of quickie examples, and then we'll call it a day. All right. And then there's one other thing that I've got to show, and then I think we're good. So if I look at this, all right, I've got the H plus concentration is 10 to the -5th. And so the pH, if I get out my calculator and you literally type in negative, you find the log button, and then it's going to give you parentheses 10 to the -5th. You hit enter, It's going to spit out 5. But the easier thing to notice is just that, look, if that's a -5 exponent, you just change the sign on it, and that's your pH, okay? Now, the pOH they've given you here is 10 to the -9th, and so the pOH is 9. pOH is exactly like pH, but instead of being the negative log of the concentration of H plus, pOH is the negative log of the concentration of OH minus. So if I give you how much OH minus we have, we just do the math. So you literally take the exponent, change the sign of it, done and done. The last column here is you just remember that if I have a pH that is less than 7, I'm an acid. And if I have a pH that is greater than 7, I'm a base. So this would be acidic. Now, one last thing before we kind of turn things over. Because we go back to my notes page from just a little bit ago, we said just a little while ago that this concentration of OH minus times the concentration of H plus was always equal to 1 times 10 to the -14. So when I take these two numbers, the concentration of H plus, which in this case was 10 to the -5th, and the concentration of OH minus, 10 to the -9th, write that a little bit better, they should always multiply together to give you 10 to the -14. That's just a property of water. And so if I look at these numbers, now we've got some blanks, all right? But we just want to remember that these exponents, the -5 and the -9, have to add up to -14. So let's fill in a couple of these here. So if I say that the pH is 7, what that's telling me is that the concentration is going to be 10, but it's not going to be 7. It's just the opposite of that sign. It's going to be 10 to the -7. And since it's concentration, it would be molar. Because these exponents have to add up to -14, right? You'll notice that the pH and the pOH, they have to add up to 14. So if the pH is 7, the pOH also has to be 7, because 7 plus 7 is 14. The concentration of OH minus, I just remember that the exponent here and the exponent that I'm getting ready to write have to add up to -14. So I'm going to go with -7 there. And if I'm right on the boundary, if my pH is 7, I'm neither acid nor base. I'm going to put you on the spot here. Do you know what I am if I'm not an acid or a base? Just kind of in the middle. It's an in word.
Neutral.
Yeah. Yep. Neutral. Neutral is going to be the word for if I'm right on the money 7. Okay. So get this a little bit finished up. So if I'm at 10 to the -4th, all right, and this is my OH concentration, you want to give it a shot. What should I write here for my pOH?
4.
Perfect. Now, if this is 10 to the -4th, this one has to be 10 to the
-10.
perfect. And then what would we write for pH?
10.
Got it. And so you just double check it. The exponents add to -14, the pH and the pOH add to 14. And if the pH is 10, what would we write over here?
Base.
Yeah. You're on it, okay? So look, that is a ridiculously oversimplified and not in-depth review of how to calculate pH, but I think it gives you enough to get this sheet going. And this is what you need to do for today. So hopefully this video helps you. And I'm going to stop recording right now.